lectures, we've been talking about Dirichlet problem and its solutions. So we were talking about classical solution, say find a harmonic function which is C2 in omega, and we can say for a moment that the closure of omega, but we can then lift this and function such that satisfies boundary condition on the boundary of omega, where C is a continuous function. And we discussed the uniqueness. So we know that if we have a solution to this problem, that solution is unique. We cannot have two solutions. And we said that if the solution exists, then and if green function exists, so then we can have this formula representation of function u in terms of the green function, right? So let me remind you that the green function in the domain is the function that satisfies this equation and equals 0 on the boundary. But so far we haven't discussed the existence of solutions. So what would be the easiest way to prove the existence? The easiest way is just to show the solution, right? To show the function that is the solution. And in some special cases it's easy to do, and one of such cases when we're dealing with a ball. So when our domain omega is a ball, and in this case I can just show you the green function, right? What the green function looks like, and then we can actually check that this will give us a solution. So we want to construct a green function. So how we can approach this? If you remember, when we were talking about green functions, about just theoretically theory of green function, we said that we can take a fundamental solution and add a function that is harmonic in omega in such a way that we have 0 on the boundary, or that's our new function equals on the boundary the values of fundamental solution on the boundary, right? With an opposite sign. And so how we can get this 0? And the idea may come from so-called method of images. So if we're talking about a fundamental solution, say, let's think in two-dimensional case, right? Fundamental solution is, has logarithmic singularity at some point, right? And if we have a certain point, say here a point where our function has a singularity, then the idea is to have a reflected point where we have also a singularity in such way that on the boundary they, so to speak, cancel each other. And how we can do this, say, now let's think again in two-dimensional case, and there we can get some hint from a complex analysis where we have a notion of symmetric with respect to a circle. So suppose we have a circle centered at point A of radius r. So r is its radius. R is its radius, and then a pair of points z and z star are called symmetric with respect to this circle, so this equation of a circle, if they have the same argument. So if they belongs to the same ray emanating from the center of the circle, and in addition, the moduli satisfy this equation. And from here, from these two equations, we can say that if Z is our original point, then symmetric point Z star can be defined by this formula, A plus R squared over complex conjugate to Z minus A, right? So we assume that Z is our complex variable and A is also a complex number. So geometrically, how we can do the construction, if say point Z is inside the circle, then we have a line through the center of the circle and point Z. Then we have a perpendicular to this line, and at the point where it intersects our circle, we draw the tangent line to the circle, and in the intersection of our original line of our ray emanating from A and this tangent, we have point Z star symmetric point. Or if our original point was here outside of the circle, first we drop a tangent to the circle and then a perpendicular. So this is an idea of how to construct symmetric points. If we're talking about n-dimensional case, then still we can use a similar construction. So I have a picture here, but let me first do the following. If we have this in mind, we will have symmetric points with respect to a ball, and we will construct our green function. So here is the our Green's function. So g of x, x naught is the point where our fundamental solution has singularity, and then we subtract from this function this function. So and this function depends on x naught. So let me show the notations. So again, we're talking about n-dimensional case. Suppose we have a ball, right? Ball centered at the origin, right? For simplicity, I take a ball centered at the origin, radius r. S would be a sphere, the boundary of this ball. So we have this sphere, and then x naught is our original point, right? So the point where our fundamental solution has singularity, and then we have a ray through this point, through the center of our ball, and this point, so to speak, a ray, right? We have this line, and then we have somewhere here x1, which is symmetric point, and by construction x1 is constructed in such a way that rho times rho1 equals r squared, right? So we have this idea. So, and what is rho? Rho is magnitude of our vector x naught. X1 is the magnitude of, so the magnitude of vector x1 is rho1. So distance from x to x naught. So x is, in general, x here is an arbitrary point in our domain omega. But I will need it soon to be located at the boundary. So I put this at the boundary, but x could be anywhere. And so x is our second variable. So r is distance from x0 to this point x. R1 is distance from x1 to the point x, and this is OX is our radius. Again, as I said, just for now I put x on the boundary. And so here, if we go back, this is our green functions. That's I'm claiming that this will be our green function. So we have fundamental solution with singularity at point x0 and minus this function. Since x1 located outside, so this function will not have singularity, and obviously, so here I wrote it differently, right? So since we're talking about spherically symmetric case, we can switch from x variables to r variables, and it is clear that, and then I switch to notations v that we used before when we were talking about spherically symmetric situation. So we have v at r minus v of rho over r over capital times r1, and so I'm saying that this is our Green's function. So for Green's function we have these two conditions, right? So this function, the first function is harmonic, unless we are at point x0, and we know, since we took fundamental solution, we know we will get this Dirichlet's delta. And the second function is also obvious that the second function would satisfy the Laplace equation, and again, singularity is outside, so this function is harmonic. So what we can see from this construction first, that our g, our function, satisfies this equation. This is the first thing we have to check. And the second is this boundary condition. So if we want to check the boundary condition, we can start with the following, right? With what we, by construction, we had these distances rho and rho1 in such a way that they satisfy this equation. And then, if we are talking about boundary condition, then x does belong to the boundary. So now just let's think of x as a point of the boundary of the sphere, and then we can consider two triangles x0 OX and the triangle x1 OX. These are two triangles. So these are similar triangles. So why they're similar? They have gamma, this angle, as a common angle. And also by construction from here, we can write that capital R to rho1 equals rho to R, right? So this is capital R to rho1 as this rho to R. And since these triangles are similar, then we can also write the ratio of the other two sides. So I took this ratio and added it as R to R1. And then from the last two, we can have the equation that links R1 and R. And so R equals this combination rho R1 over capital R equals to our little r. So we can see that what we have here is on the boundary, right? On the boundary, this equals to R. So on the boundary, we have these two functions equal to each other, and therefore function g vanishes on the boundary. So we actually have checked that the function that we wrote here is the green function for the ball. So we just constructed our green function. So now our goal is to show that this function, this representation would be a solution. This solution, we know the solution is unique when we are trying to find solution to the problem when U is harmonic in the ball, centered at the origin of radius r, on the sphere boundary of this ball satisfy this condition, and we are talking about functions, C2 functions. And before showing that this is indeed the solution, let's just simplify this formula, right? So now here I replaced just an abstract boundary with our sphere, and now we know function g. So let's just specify this expression, derive a formula, and then we will prove that this formula gives us the solution to the problem. So we need to compute the derivative dg d nu. So our function g is here, it's difference of these two functions as we just got, and when we want to compute the derivative with respect to outward normal, we use the chain rule, so it will be v prime with respect to r, its argument, and dr d nu minus v prime with respect to its argument, times we use chain rule rho r dr1 d nu. And then if we recall that when we are on the boundary we have this condition, so this can be replaced on the boundary with r, and our dg d nu is v prime of r dr d nu minus rho over capital R dr1 d nu. And now let's just compute this derivative. We can recall that when we want to compute the directional derivative, it will be a dot product of the gradient and unit normal, and it is convenient now to rewrite this as magnitudes of two vectors times cosine beta. So what is beta? Beta is the angle between this is my direction of the normal, and this is direction of x1 x of this vector. So beta is angle between this and this vector, and also this beta, let's call it beta sub 0. Beta sub 0 is this angle as well, right, as a vertical angle. And similarly, we can compute dr1 d nu, and that would be also a cosine. So here I have shown that both vectors here, both magnitudes equals to 1, right? Obviously, nu u is has magnitude 1 because we just constructed it this way, right? It's vector x over R, and gradient R, it would be this vector that is given here. You can easily check. So here it's written what R is, so you can easily check that magnitudes magnitudes of both vectors equals 1, and the same calculations for the second derivative will give us cosine beta 1, then where beta 1 is the angle between the outward normal and vector x, x1, x, right? This vector. So angle will be here. Before I just had wrong picture here, and so then inside this beta 1 will be this angle. So now what we can do, we can use the laws of cosines. They are written here. So we, instead of these newly introduced cosines or angles beta 1 and beta sub 0, we can go back to our notations in terms of r's and rho's. So here I just continued this expression dg d nu. It is here. It will be v prime of r, and then I replace these two expressions with cosines. It will be cosine beta 1 minus rho over capital R cosine beta 0 minus cosine beta 1. And then we recall what v of R is. It's our spherically symmetric fundamental solution. V of R in when n equals to is logarithmic function, when n greater than 2, it is this is n even by this formula, but when we compute derivative with respect to r, we can use the same formula for both cases. Omega n here is the surface area of our sphere, and so I replace v prime r with this expression, and cosine beta sub 0 and beta sub 1 I replace using the laws of cosine, and at this moment we have dg d nu written as this expression. So minor thing left, just to simplify this formula, and we will be done with our derivation. To simplify this, let's look at the second part, right, and simplify it first. And of course I need to comment that I called omega n surface area of our sphere, surface area of the unit sphere, right? Our as radius r. Okay, so here I just copied this expression, so rho over r. Let's multiply and divide by rho, which you can see in red here, and let's also replace here. We have r1, and r1 and r are related to each other using this equation, so we will replace r1 in terms of rho, which is here, and then rho 1 and rho are linked through this equation, right? So instead of rho 1 we can write r squared over rho. So we replace it here as well, and in the bottom we have r1. We replace it using this formula, and then we can so here we will have rho squared. We will distribute it, which will cancel so this rho squared and this will be cancelled. So we will have r squared rho squared, and here we have to, of course, multiply, right? So what we did, we multiplied by, sorry, rho squared. So we have this expression now, and then we can cancel r capital squared here. So this, it has this in every term, and we will end up with this expression. And so this was simplification of this last term, and now let's collect everything together. So it will be dg d nu 1 over omega n r n to the minus 1 first term minus a second term, and then a common denominator will give us this expression. So this would be our dg d nu, and finally our integral can be simplified or specified to this formula. We can pull this out, so it will be as a constant r squared minus rho squared over omega n r integral over sphere psi over r to the n, right? And we integrate over the sphere r to the n, and r to the n, r can be replaced using, again, a law of cosines, but now here, so this is our r, right? So from this triangle we can introduce angle gamma between this direction from O to center to x, and direction from center to x naught, right? These triangles, so gamma would be this angle, and then instead of r to the n, we will have this long expression r squared plus rho squared minus 2r rho cosine gamma to the power n over 2. So you can see this expression as well. In some textbooks you can find this expression when people use, say, in two-dimensional separation of variables, and they come with cosine, so you can compare formulas. And so we have this formula. It calls Poisson's integral formula, or Poisson's formula, or Poisson's integral, so you can see different combinations. And now we have representation. What's left is to prove actually that this is the solution to our problem. Okay, now let's show that this Poisson's integral formula represents actually the solution. Right, so the claim is that this formula solves this Dirichlet problem for a ball for any continuous function psi. This is our claim. So what do we need to do? We need to check two conditions. First, that this function is harmonic, and second, that it satisfies the boundary condition. So to show harmonicity, it would be easy, instead of doing direct computations, it would be easy to recall that what we have here is dg d nu, right? So g is our Green's function. So if we remember that fact, then also we have to recall that g is symmetric. It's symmetric with respect to x naught, so if we interchange them, function remains the same. And we discussed that when we've been talking about theory of Green's function. And having said that, to show harmonicity, we can compute Laplacian of G with respect to variables x, right? So G depends on two sets, x and x0. When x0 is fixed and x is a variable delta G equal 0, and when x is fixed and x0 is our variable delta G equals 0, whenever x not equal x0. And so let's differentiate, compute the Laplacian with respect to variables x0 from both parts of this equation. And since integration is with respect to x, when we compute Laplacian with respect to x0, we can pull it inside of the integral, and here we will have 0 when our point x0 is inside the ball, right? So our point x here is on the boundary, x0 inside the ball, they are not equal to each other, so we are getting 0. And so since delta G is 0, then delta U is 0 as well. So this part is done, right? So we checked harmonicity. Now we have to check the boundary condition. So the boundary condition, we want to show that if we have our point x0, and when x0 approaches the boundary, our function u at x0 approaches value psi x hat. X hat is a point on the boundary, on the sphere. So first let's comment that we can choose x hat here on the same radius as x0. Why? Because if, say, instead of x hat we had x tilde is a point that is not on the radius, then we can write that absolute value of u of x0 minus psi of x tilde is less or equal than u at x0 minus u at psi x hat plus absolute value of psi x hat minus psi of x tilde, right? We can write this, and then due to continuity of function psi, right? Function psi is continuous. We know that when point, say, x hat goes to point x tilde, psi of x hat goes to, or psi of x tilde goes to psi, psi of x hat goes to psi of x tilde, right? So since by continuity, small change in variables leads to small change in function. So this would be would go to 0 in this case. That is why we can forget about this part. We need to prove at least this case when x0 and x located on the same radius. Okay, so it would be convenient for our computations to notice this fact. So when we were talking about Dirichlet problem, we just established that if solution exists, it's unique. So we know uniqueness, and from uniqueness we can get something. So suppose that we are considering this Dirichlet problem when our boundary condition is just a constant. Let's call this constant c. And then it is easy to check that solution when u identically equals to c in our domain would be solution to this problem, the solution, because every constant is harmonic, right? When we differentiate, we get 0, and constant is this constant everywhere, including the boundary. So we have this fact. And specifically, let's plug for C number, say number 1, right? So if C is 1, then our solution is 1. And now let's look at our formula, this one. If we have this formula, if we know that C is a constant, it's 1, so we plug 1 here, and we know that in this case solution, we just said, solution would be the same constant, 1, so U at x0 would be also 1. Then we will have this formula that 1 equals 1 over omega n r square minus rho square over Rn ds. So we have this formula. And we said that we will use it. And another formula that we can get from there, if as this constant, we take psi at x hat, right? So if x hat is fixed, psi at x hat is a constant, so then we can plug this constant again here and there. And so we will have that psi at x hat is 1 over omega n r integral, and here we have psi at x hat. And so what do we need to estimate? We need to estimate this, right? We agreed about this term. We just need to estimate this. Fine. So I wrote his, it's here, u at x0 minus psi at x hat. We need to evaluate this. And then what we do, we replace u at x0 using this formula, right? We plug it here. And psi hat, psi of x hat, we replace with this formula. So here we will have absolute value of the difference of two integrals, right? So we have two integrals, and we can combine these two integrals as one, right, integral, and then we know that modulus absolute value of the integral less or equal than absolute value of the integrand of inside. So this will lead us to the following inequality, right? So it will be integral, and then here we will have absolute value of the difference psi minus psi hat. So to finish showing that u at x0 approaches psi at x hat when x0 approaches x hat, we will split our sphere into two parts. So one of them we will call omega 2, one of omega 1. So how we will do that? We will consider a ball centered at point x hat. X hat belongs to the boundary, and take radius of this ball delta, and delta would be a sufficiently small number, and this ball would be in Rn, and where Rnx in the x space. And then we will consider intersection of this ball with our sphere. So I wrote it here. And the part where sphere intersect this ball, let's call omega 1, and the rest of it, the rest of our sphere, we will call omega 2. And then, so we are here, right? We have integral over s. So then we split this integral into two. So we split this integral into two. I'm continuing here. Let's call them I1 and I2. And I1 is integral over omega 1, and I2 integral over omega 2. So, and I wrote this here. It's exactly the same integral as we had here. So two integrals. So let's first look at this integral I2, where it means that we're integrating along omega 2, part of the sphere, where x is outside of this ball. So x is outside, say x is somewhere here, right? So here we have our point x. Then what happens when x naught approaches x hat? Let's look at this expression. So here we have r squared minus rho, and rho is this distance from 0 to x naught, and r is our radius. So when x naught approaches x hat, this difference goes to 0, right? When x naught approaches x hat. Then what is this? These are just given constants. Here we have psi at x minus psi at x hat. We know psi is continuous function, and it is bounded on the sphere. So here we will get just a constant. So what happens? What is r? R is, let me remind you, r is our distance from x naught to x, and x is outside of this small ball, right? So when we're talking about distance, this distance will not be 0. It will be actually bigger. This distance r would be bigger than some constant which is bigger than 0, some positive constant. So what do we have from here? From here we have that here we have some constants, and this thing goes to 0, so it means that the entire integral goes to 0 when x naught approaches x hat, right? So this integral we discussed. Now let's look at the second integral. At the second integral, right? So we discussed the case when x is outside of this ball. Now, what if x inside? So x is somewhere inside. So difference would be with Rn, right? Now we cannot say that r is bigger than some constant. So what we will do here? So here, so this is, we can take this absolute value. We can pull out, we can find its maximum, right? We can find its maximum in the domain of omega and pull this out of the integral. And these constants I will pull back in. So why? Because then I will pull, and not only I will pull them back in, I will replace integral over omega 1 part of so part of the sphere, and with integral along the whole sphere. So then in this case, then integral will become only bigger. And then we know that this integral equals to 1. So finally we will have that from here to here we have just maximum of absolute value of the difference psi(x minus psi(x hat, and maximum on omega 1, right? And then we know that our function psi is continuous function. So for every epsilon, given positive number epsilon, small one, we can find such a delta, such a small radius, that if distance between x0 and x hat is smaller than delta, then this will be smaller than epsilon. This finishes the proof, so we have established that when x0 goes to the boundary, in this limit, u at x0 approaches the boundary function. From Poisson's integral formula, we can get an inequality that is called Harnack's inequality. So the theorem states as if we have a function u, which is harmonic in a ball and is C2 function in the closure of the ball, and in addition, if this is non-negative in this ball, then for any point x0 in the ball we have this inequality. And here x0 is any point in the ball, right? U at 0, 0 is the center of the ball, r as earlier radius of the ball, rho is the distance from x0 to the center. And then we can have this inequality which helps us or gives us an estimate or evaluate value of our function u at any point of the ball in terms of values at the center, right? So or if we divide everything, if u of 0 not 0 divide, so the ratio of u of x0 to u at x0 to u at 0 can be estimated. And so how we can get this inequality? We consider the picture similar to what we had earlier. O is the center, x0, and let's look at this triangle x0 OX, and from this triangle we can write this inequality simple, that r, little r, is bigger than the difference, capital R and rho, and smaller than the sum. And then if we just raise everything to the power n, we will keep the same inequality, and then if we invert, we have to switch the inequality, switch the sides, and then we multiply everything by these positive numbers. So we'll keep the inequality, and then if we take into consideration that u is non-negative, and then we multiply just everything by psi over omega r, and then integrate along the sphere. So then what we will get here in the center? In the center, we will get exactly this formula. So we will get exactly u at x naught, and here we will get I put here some, I call them constants C1 and C2, just to make the expression shorter, and we will get expressions that allow us to use spherical mean value property that we discussed earlier. So using this formula and plugging everything in, we will be able to get this inequality that we wanted to prove. And so what is the meaning? So basically we can say that values at all different points of a ball are not that different from each other. They're, so to speak, pretty close, and because of these estimates. And another thing that we can notice here, if you look at this inequality and now send r to infinity, so assume that r is huge. If r goes to infinity, right, in the limit, if you look at this number, then in the limits, so here we have r to the n minus 1, and here we have r to the n minus 1. So in the limit it will go to 1. And similar situation will be here. So these both factors will go to 1. So what we will have? We will have that u at any point in the ball will be bigger or equal than value at the center, and smaller or equal value at the center, which means that our function is constant, right? So again, if our function is positive in any bounded domain of the entire space, and then Harnack inequality tells us that such function is constant. Thank you.